Welcome to The Explainer. Today, we're going to talk about something pretty amazing, biomass. We're talking about how we can take everyday organic stuff, farm scraps, city trash, and turn it into a really powerful source of fuel. All right, so here's how we're going to break it all down. First, we'll get a handle on what biomass actually is. Then, we're going to look at two totally different ways to get fuel out of it. One's all about biology, the other uses some serious heat. We'll even compare the specific tech involved, and at the end, see how they really stack up. Okay, first things first. What even is biomass? Before we jump into all the cool high-tech conversion stuff, let's really get to know our starting material, our fuel source, and the too many ways we can unlock all that energy locked inside. That's a fantastic question, right? And the answer? Well, it's literally all around us. The key to all this is biomass. I'm talking about the organic stuff you find on farms, in forests, heck, even in your own trash can. So here's a simple way to think about it. Plants are basically little solar-powered batteries. Seriously, they soak up the sun's energy through photosynthesis and just store it. What biomass technology does is it gives us the key to unlock that power, even way after the plant's been harvested or thrown out. And this is where it gets really interesting, because we basically have a choice to make. There are two main paths we can go down. We can either use biology, let microorganisms do their slow and steady thing, or we can go the thermochemical route and use some intense, rapid heat. Both start with the same stuff, biomass, but they take it on completely different journeys. All right, let's check out that first pathway. This one is all about biology, and we're going to see how some of nature's tiniest workers, microorganisms, do some seriously heavy lifting when it comes to making energy. Okay, so this process has a name, anaerobic digestion. It sounds complicated, but it's not. It's basically just bacteria munching away on organic waste in a place with zero oxygen. What do we get out of it? Biogas. And this biogas is mostly methane and carbon dioxide, which is super similar to the natural gas a lot of us use to heat our homes or cook our food. Now, this is pretty cool. It's not as simple as just, tossing a bunch of waste into a tank and hoping for the best. No. To really get the most energy out, you've got to become a kind of microbe manager. You need to get the feeding rate just right, give them the perfect diet, that's that carbon to nitrogen ratio you see, and create the perfect little home for them with the right pH and temperature. It's all about keeping those bacteria happy and working hard. Okay, let's totally switch gears now. We're going to leave the world of biology behind for a bit and step into the furnace. It's time to look at a high-temperature approach for turning that biomass into fuel. So instead of that slow, weeks-long digestion process, gasification uses intense heat to break down biomass, and it does it fast. Now, the trick is to carefully limit the oxygen. If you don't, you just get fire, right? You get combustion. But by starving it of oxygen, we force a different kind of chemical reaction, one that turns solid biomass into a useful fuel called producer gas. And that's mostly a mix of carbon monoxide, hydrogen, and methane. And here's a great look at how that works. This is a diagram of a classic fixed-bed gasifier. You feed the biomass in at the top, and it slowly makes its way down through these different zones. First, at the top, it dries out. Then it hits the pyrolysis zone, where it really starts to break down. And then, deeper down, in those combustion and reduction zones, that's where the magic happens. The crucial chemical reactions kick in with just a little bit of air or steam, creating that producer gas. The gas gets pulled out, and all you're left with at the bottom is ash. Pretty neat. But wait, there's more. Even with this one type of gasifier, there are some really important design tweaks. And maybe the simplest but most critical is just which way the air is flowing. This one little change gives us two totally different setups. So this really comes down to a classic engineering choice. On one side, you've got the updraft gasifier. Here, the air flows up as the fuel moves down. It's a simple design for sure, but the big problem is that the gas picks up all these sticky tars on its way out. Yuck. On the other hand, you have the downdraft gasifier. Here, the air and the gas both flow down together with the fuel. And this is clever because it forces all those tars through the super hot combustion zone, which basically cracks them apart into a much simpler, cleaner gas. The takeaway, downdraft gasifiers give you a much higher quality fuel.
Okay, so we've looked at the biological path and the thermochemical path. Now let's bring it all home. We're going to put these two powerful technologies side by side and get the full picture.
And this table just lays it all out perfectly. You've got biogas production. That's your slow, wet, biological process. It needs a total absence of oxygen, and it's perfect for stuff like manure or food waste. Then you've got thermal gasification. That's the fast, dry, high-heat method. It just needs a little bit of oxygen, and it's much better for things like wood chips or dry farm waste. At the end of the day, they're just two different tools for the exact same job, turning waste into fuel.
So as we've seen, the science is solid. The technologies are definitely well understood. We know we can use biology or we can use chemistry, but that leaves us with one last really big question, doesn't it? If the fuel source is literally everywhere and we know how to convert it, what's stopping biomass from powering our world? What are those real-world hurdles, the economic ones, the logistical ones, that we still have to figure out?